5 is our last section of new material in Chapter 3. And we're going to do two things in this section that are related, but they're different. One says mental math, and the other one says estimation. Okay? So mental math means you do it in your head. Estimation means it's not going to be exact. So there is mental math we do in our head that's exact, and there's mental math that we do that's an estimation. So there's two pieces of what we're doing in this section that are related, but they're not the same. All right, so to start with, we're going to take a look at mental mathematics with addition. Okay, so we're taking a look at an algorithm that's referring to adding from left to right. And we've talked about this idea before, but we're going to actually do this as we, we can see it in a little bit different light, I guess you could say, than we've looked at it before. All right, so one way to do this when we add from left to right is we consider only the left-hand value. That is, if you're looking at the 4 and the 3, we recognize that the 4 actually means 40 and the 3 actually means 30. So when we do this, we're actually looking at the 40 plus the 30 together, which gives us 70. And then we're looking at the 6 and the 8, and 6 and 8 here really means 6 and 8. And 6 and 8 are 14, and then if you combine the 70 and the 14, you get 84. Hang on a sec. We already did this once, but for some reason it's not lining up again. Alright, so when we're working with a 2-digit number, this kind of works nicely. We don't have to keep a lot in our head to do this, but you're thinking of sort of like breaking it apart into pieces. The next one's called breaking up and bridging. And breaking up and bridging, what it does is it takes the whole first value, 46, okay? And instead of adding 38 to it, it only adds the 3 part of it to it. So just like we established a moment ago, the 3 actually means 30. So this is in essence taking the 46 and adding 30 to it, and recognizing that that gives us 76. Now I'm not done at the point when I get 76 there, right? I still have to add something to it. I have to add the 8. So I need to add 8 onto that to give me then 84, same 84 as before. So you're breaking that 38 up into 2 pieces. That's what you're doing. You're breaking it apart. And then you're bridging by adding that piece back in that you've sort of left out in the middle of the part, or in the middle of the process. That's called breaking up and bridging. Now, I know this is mental math, and I just wrote all kinds of stuff down. So that sounds sort of weird. It's mental math because you should be able to do all of this in your head. But I can't see what's going on in your head, and I've talked about this before. But this is the process that your head is doing, if you will, on paper. Does that make sense? And the only way that I have to know that this is what your head's doing is for you to show it to me on paper. So yes, this is mental math. This is the stuff you should be able to do at the grocery store, given that the values of things are nice numbers and not weird decimal points at the end, of course. But this is the kind of math you should be able to do in your head. But these are different processes by which you can do it in your head. Okay? All right, let's do another one. I like the trading off method. So the trading off method feels a lot like one that we've seen before. So let me do it for you, and you can tell me if you can identify which one it is like that we've done before. All right, so what you can do is you can take the 46, and you can add a value that's really, or the 38, it doesn't really matter. Add a value that's really nice to one of them that turns them into a multiple of 10. So if you decide to start with the 46, what could you add to 46 that would make it really nice? 4. And if you started with the 38, what could you add to the 38? 2. So it doesn't matter which one you choose, but you're trying to turn one of those numbers into a nice, pretty multiple of 10. That's your goal. Okay? I'm going to do the 2 just because it's smaller, not because it matters. I can't figure out why this is not working today. Just estimate off. Okay, so we'll add 2 here. Trading off, though, means that if I add 2 here, I have to subtract 2 up here. So adding 1 to one piece subtracts 1 from another piece. And this is adding 2 to one piece subtracts 2 from the other piece. So if I take 46 and I subtract 2, what do I get? 44. And if I take 38 and I add 2, I get 40. And it's easier to add 44 and 40 than it is 46 and 38. So you're turning one of them, and it really, again, doesn't matter which one, into a multiple of 10. What does this feel like? We had a method that was it? Equal additions. What's different about this than equal additions? Okay, so this one we're adding and we're subtracting. With equal additions, we added both. Why? What were we doing when we did equal additions? We were attempting to not borrow because we were subtracting. Equal additions is a subtraction method. Okay, so if you're subtracting two values, if you take a little bit off of each piece, then you have just changed both of them down by the same amount. They still differ by the same amount. Here, basically what you're doing is imagining that you have two piles, right? Here's 46 in this pile, and I have 38 in this pile. And I'm saying, well, if I take 2 away from here and put it over here, I still have the same combined total. But then my addition works easier because I'm adding things together. So you're sort of regrouping at least a little bit here when you're doing this kind of a method. You're taking something from one piece and putting it over here. Compatible numbers is a really nice strategy as well. So compatible numbers, the goal again, just like in the last ones, is to look for things that are adding together to a nice value. So somebody give me an example. Give me 2 numbers here that add together to a nice value. Okay, my goodness. All right, somebody said 40. Let's try 40. 40 and what? 40 and 60. Why are 40 and 60 nice? They make 100. So these two are considered compatible numbers. They make 100. Tell me another pair. 30 and 70 are compatible numbers because, again, they combine to make a number that is 100. And then the last number doesn't have a pair for it, so he's just all in his little lonesome bag. But the total ends up being 250. So you're just looking to group things together that make addition easier. I do this at the grocery store. When I add things up, I'll say, well, that's about 4 and that's about 6, so I'll add those numbers together before I add in the macaroni with 33 cents. Right? I mean, I don't want to do the addition in a harder way as possible. I'll sort of group things together into something that adds up to something nice. That's all compatible numbers is. All right. Now, this one, these numbers are not compatible. They do not add up to 100, right? But we can make them into numbers that are compatible. That is, we can turn them around so it actually becomes something that's easier to add. So how do we do that? Well, if I were working with the 35, what would be the compatible number to 35? What would it be? No, compatible means it has to add up to something that's a really nice number. In particular, the number in the last section was what? In the last slide. 100 over here. The number that the compatible numbers group to is number 100, right? So if I consider the 35, what would I have to add to 35 to get to 100? 65. And the reason I like that 65 and I'm sort of drawn to that is because when I add the 35 and the 65 together, this keeps going downhill. I get the 100, and I really am awfully close to the 68. How far off am I? I'm just 3 off, right? So this is only 103. $68 is 65 plus 3. First I added the 65 because it made it to a nice number 100. So it turned it into a number that's nice to work with. And then I added what's left over afterwards. Make sense? Now, there's nothing special about the number 100. The reason I chose the number 100 is because hopefully when you look at 35 and 68, you say, that's awfully close to 100. It should sort of feel that way when you look at those numbers. They're pretty close to 100. So when I chose the 65, I did it because I knew that my answer should be pretty close to 100. Does that make sense? So it's not always 100. It may not be a 100 in the future, but it was for this one because 65 and 35 gave me that value, which was awfully close to where it be. All right, let's do subtraction next. Okay, we've got a breaking up and bridging method for subtraction. So what did we do when we did breaking up and bridging for addition? Can you flip back to that first page and tell me how we break things up and bridge? What did we do? We broke up that last number. All right, we gotta try this one more time. I've never had it lose its alignment in the middle. Working. Alright, so Angela, you told me we broke up the second one, right? So how could I break up 38? Okay, so I can still start with 46 and I can break it up to be minus my 30. So I haven't done anything with 8 yet. I'm just subtracting the 30 part of this first. So what would 46 minus 30 be? 16. Now we recognize we're not done. I still need to take off 8 more. But once I get down to a smaller number, 16 minus 8, that's probably one of those addition facts that you memorized on some flashcard at some point in your life, right? And that gives you 8. So you're breaking apart the second value to do the subtraction, and then you're bridging with that last piece. Trading off. Okay, so what we're about to do with trading off is equivalent. This is equivalent to equal additions. Remember that method? We just talked about it a minute ago. I've got 36 and 46 and 38. I don't really want to subtract 38. Why don't I want to subtract 38? Because the 8. Yeah, the 8's not so nice. I'd have to borrow, right? And so that's the part that's not so nice. So what would be better or nicer to subtract than 38? 40 would. So Marilee, what would I have to add to the 38 to get to my 40? 2. Now, in this trading off method with addition, I would add 2 and I'd subtract 2. They complement one another, right? But this is a subtraction problem. So I add 2 to the top one as well. Very good, Hannah. So I'm adding 2 to both of those pieces. Okay. So in this case, it's sort of like having $46 here and $38 here. And I'm saying, okay, but if I bumped them both up $2, it'd still be different by the same amount. I've talked about before, I don't know if I've done it in this class or not, it'd be like me standing here and my little daughter standing here, and if we both put on 2-inch heels, we'd still be the same difference in height. Wouldn't change anything, right? That's the same thing here. So if I add 46 plus 2, I get 48. And if I add 38 plus 2, I get 40. And then I subtract and I have the same 8 that I've had on the examples above. All right. We have one more in subtraction. Yeah. And this one is drop to zeros. So we're taking a look at 4,600 and 3,400. So the zeros don't really affect the answer, right? I mean, they're a part of the answer, but they don't really affect the processing to get there. We can sort of ignore them for all intents and purposes. They don't really matter a lot. So we can sort of ignore them, and we can only look at these pieces. What do you have if you've got 46 minus 34? It's 12. But my answer should then be 1,200. So I'm ignoring the zeros because they match up. They don't really affect the answer. And I can do the subtraction as 12, and then I've got the 100 part of it on there because the original question was hundreds. It's almost like writing out the word hundreds next week. It's a unit like meter or something like that. All right, let's do some multiplication and division. Multiplication. We're still working on mental math where it's exact. We're not estimating yet. Promise we're getting there. We're not estimating just yet. All right, so mental math with multiplication. The first one is called front-end multiplying. So what you do with front-end multiplying is you multiply the first digit, like this is the number 46, so the first digit is the 4, and you recognize that 4 actually means 40. So you take the 4, understanding that 4 means 40, and you multiply it by the single digit 5 that this whole thing's being multiplied by. So what's 40 times 5? 200. And then you do the second one. Okay, or the third one, or whatever's next. You know, we keep going down the line. Okay, well then I've also got 6 times 5, which is 30. So the total is 230. And again, you're sort of seeing that this has sort of a left to right movement, right? Because we kind of think that way with the way that we read. This has sort of that same feel to it a little bit. We've got to go through compatible numbers here, but compatible numbers with multiplication are different than compatible numbers with addition. When we were doing compatible numbers with addition, we were looking at what numbers added together nicely, right? So what are we going to do when we're looking for multiplication compatible numbers? multiply nicely. Now I see lots of I see lots of small numbers here, but not all of them are as nice as others when they multiply. Can somebody give me one pair of numbers that multiply to a very nice number? Somebody said 2 and 5. I don't care which 2 and 5 you use, but 2 and 5 are really nice. Why? They give us 10, and 10's a nice number because it's got a 0 in it. I mean, that's really just all there is to it, right? I like numbers with zeros. Zeros make things add nice, they make things multiply nice. So if I compile these together, make these two, multiply those two first, then I'm going to have a nicer number to work with. What else would be nice here? You could use 8 and 5, or you could use 4 and 5. Either one are equally nice. Why? What does 8 and 5 give you, Marilyn? 40, and it's nice because it has a 0 in it. And what about 4 and 5? 20, and it's nice because it also has a 0 in it. So you can pick whatever ones you want. I'm going to use Marilyn's suggestion because I heard hers first. So if I use 8 and 5, I get 40. And then I have my same 4 at the front. Okay, so I've reduced this from being a multiplication of 5 numbers to a multiplication of 3 numbers. And in fact, 2 of the numbers are really, really nice because they're multiples of 10. So again, it doesn't matter what order you go in here. I'm going to start at the back because I like multiplying by 10. So what happens when I get 40 times 10? That's 400. And then times my 4 is 1,600. So you're just breaking them apart in a way that's friendlier to work with. That's all you're doing. You're making the work as easy on yourself as possible. Okay? All right, the next one's interesting. It says thinking money. That's the title of this mental math method. So what in the world do you think it means when it says 46 times 5 and it says thinking money? How in the world could you relate that problem to money? Nickels. Very good. Thank you, Nicole. This 5 is nickels. So this is like having 46 nickels. Now think about this with me. If you had 46 nickels, you can count the nickels and you can multiply and so forth, but what are easier to work with than nickels? Quarters are, something else even. Dimes is where I'm headed. Dimes are really nice to work with. Why? Because it's a multiple of 10. You guys kind of get the idea that we like 10? It's good. Okay. Yeah, so how could I say, if I've got 46 nickels and I want to turn it into dimes, what do I get? This is 23 dimes. Well, how much is 23 dimes? $2.30. But we don't actually have the decimals or anything here, so this is 230. We understand that that would be $2.30, right? But we aren't working with decimals in the problem. So this is 230. Is that okay? Make sense? You're turning it into something that multiplies out easier. And dealing with money is really nice. How about this one? 44 times 25. What in the world is it talking about when it says thinking money here? That's quarters. So this is how many quarters? This is 44 quarters. All right, now, what's easier to work with than 44 quarters? How many dollars? This would be $11. So how much would $11 be when we're working with it in this fashion? What are we getting for our final answer? This is 1,100. It's almost like considering it as though it's in pennies, right? $1,100 under pennies. So this is 1,100. I don't know about you, but if I were to actually have done this problem out with times 25, it would have taken me a lot longer than that. But if I think of it in money, you guys, I mean, you've done it in no time at all, aren't you? You really were. All right, we're doing division. The first one is breaking up the dividend. So when you take a look at breaking up the dividend, it looks like this. So we're going to write it kind of like we do our normal division process of how we sort of think about it. But we're breaking it apart right here. So you're going to break it apart there. Why would that be nice? Yeah, they're both multiples of 9, right? So Katie told me 63 and 9, I would put a 7 here. And then the 9 and the 18, I would give me a 2. Now is this 72? It's 702, so we do have to be a little bit careful, right? That this is actually at 6,300, so this is interpreting this like, in fact, I'll write it out that way too, just so you can see it a little bit better. Interpreting this as 6,300 and 18. Sorry, it's still all off. So 6,300 gives me 700, and the 18 gives me 2, so there's the 702. That's why that's happening there. You do have to be really careful when you break apart that you don't misunderstand that that's not 72. Compatible numbers. Now, if I were to try to do something like this with this directly, 4 is not a good break spot, right? Because 5 does not go into 4, although 25 would have been fine. But it doesn't work quite as cleanly as last one, right? That isn't very helpful. But it's still the right method. Instead, what we want to think about is we want to think about it like we did over here. 4 is actually the number 400. And I can divide 400 by 5 very nicely. How much will that go in? 80, right? So if you're taking a look at the first two numbers instead of just the first number, 5 will go into 48 times with this remainder of 0. And then how many times will 5 go into my 25? 5 times. So my result on this one is actually 85 by breaking it into pieces that are compatible. Okay. Now what are you doing? This is estimation, which means my answers are not going to be exact. That's not my goal. My goal is, this is the grocery store math you do all the time, right? You want to make sure when you get to the register you actually have enough to cover your purchases. This is that kind of work, okay? So the first one is called front-end estimation with adjustment. Now you've seen the phrase front-end estimation before. I think you saw it on the test, didn't you? No? Not in this class, it's in the other class? Okay. Front-end estimation, what it does is it looks at only the first digit and it adds those together. It ignores everything else, okay? So front-end estimation adds all of this together first. So what do you get when you add 300, 400, and 200? 900, okay? That's the front-end part. So the front-end part is this part. The adjustment part means that we're going to look for compatible numbers. That is, if I were to be able to join two of these, or if I had a whole long list of them or something, several of them together, could I sort of estimate what's left over afterwards? What adjustment do I have? Because obviously changing the number 462 down to 400, which is essentially what I did here, well, that didn't estimate it very well, right? I mean, 462 is closer to 500 than it was to 400. So maybe there was a way that we could have done that better. So taking a look at these numbers over here, are any of those nicely compatible or nearly so? Yeah, the 62, say it again for me, Hannah.
62 and 32 is almost 100.
That's almost 100, isn't it? It's close. Remember the goal is estimation here? This is close to 100. So front-end estimation takes that number and said, I'm almost at 100 there. And all it does is it adds this one, and if you've got a little bit left over here that you want to just completely sort of throw into, that's okay. Because you can add those two numbers together pretty well now because everything except for the 25 is a multiple of 10. So what happens when I take the 900, the 100, and the 25? What do I get? It's 1,025. Is it exact? No, it isn't. Do I care? No, not really. Because as long as I get up to the register and I've got something close to this, it's probably going to be okay. I've estimated. It's all right. Got a little tax there too. But yeah, that would be a lot of groceries there. Yeah. A little high for that. Maybe it means $10.25 and we're ignoring the decimals. Can we do that? Okay, we can do that. All right, grouping nice numbers. All right, so this is the compatible numbers idea. We're looking for things that group together and they're nearly maybe 100. 100's often a number that's nice to go to. Maybe they're nearly 1,000 if we were dealing with bigger numbers or something like that. So do you see any pairs of these that would nicely group together? Okay, 35 and 55. There's more than one way to do this too. So if you don't see something the same way we do, that's okay. What would you like to say 35 and 55 almost is? 100? It's about 100. Okay, what else? The 42 and the 64 are awfully close to another 100. And the 71's sort of a little bit off, but it's about 70. So if I were to add these together, I get 270. So this would be like physically moving those objects around in the cart and saying, okay, this item is 42 cents and this item is 64 cents, that's about $1. And this item is 35 cents and this item is 55 cents, that's about $1. And then I've got this 70 cent whatever left over, and it's about $2.70. Make sense? Because your goal is to estimate, and that will do that for that one. Clustering is another nice feature. So clustering is taking a look, and this method, none of these methods work for every list of numbers. Maybe I just need to say that right now. They just don't. Okay, so if I were to ask you to do this number set with compatible numbers, it may not work very well with compatible numbers. But this number set works really well with clustering. Clustering is when you have a whole bunch of numbers really like surrounding another nice number. Take a look at that. I've got 442, 538, 457, 554, 497. All of those numbers are about 500. Awfully close, right? They're sort of clustering around a centralized number. If you were to sort of place them all on a number line, they'd sort of all be grouped in there right around the number 500. So this is about 500. They're all approximately 500. So what could I do instead of adding together all of these numbers if I'm just interested in estimating? 500 times 5, which would give me, good, 2,500. So this is 2,500 is approximately what those 5 numbers are added together. Now, oh, sorry, Kenny, yes?
When we do these kind of problems, we need to write, because like I remember in like algebra and stuff, we had to write like the little like about symbol saying like we estimated.
Yeah, so the approximation symbol would go right here if you're going to write that. It wouldn't actually go right here because these two are exactly equal.
Right.
Yes, but this is this right here is approximately equal to that. So yes, it's a good idea. It shouldn't be all that crucial in the ones you're doing because they're never given an option. You're not going to be like find it or approximate it. It's going to tell you which one to do, which means that inherent in what you're doing is going to be that you've approximated or that you found it exactly. So it isn't a big sticking point on most of the ones. I don't think you're going to see it be a question. All right, rounding is another one. Now, this is very vague because it just says rounding. So what we're going to do is we're going to take a look at rounding in a couple different ways. I'm going to round first. We're going to do the thousands place, and then we'll do the hundreds place as a couple options. It doesn't matter if you're not told how to round, you get pick. It doesn't matter. But I want to show you a couple different options depending on what you want to do. All right, so if you were rounding to the thousands, and if you have the number 4,789, what will that round to if you're rounding to the thousands place? That is 5,000. So remember that what you do is you look at the number right after the place you're looking at, which is a 7. If it's 5 or up, you round the 4 here, gets rounded up. And if it's a 4 or below, then the 4 stays a 4. All right, how about 3148, 3,148? Right, that's 3,000. So this 1 right here is the number that makes that decision. So the 3 stays a 3. Keep it red. So if you were rounding to the thousands place, this is approximately 8,000. Now, if you're rounding to the hundreds place, that changes things because now you're looking in the tens place to make the decision about the hundreds place. So what would 4789 be if you rounded the hundreds place? That is 4,800. And what would 3148 be? 3,100. And what happens if you add those together? 7,900. It's close to the 8,000. It doesn't have to be all that close. It wouldn't necessarily have to be. But on this one, it really doesn't matter a great deal on which one you go with. Yes, Gary?
This kind of goes back kind of to other questions. So like on a test and everything, these are all of our answers kind of different.
They could.
Okay.
Yes. So a lot of things I like to do when I ask these is ask you to explain your reasoning, and that's going to give me a lot of indication as to what you're doing and how you're thinking about it. Yeah. But But yes, your answer could look very different than Becca's answer, and they could both be still 100% correct. All right. Using the range. Okay, we have 2 slides left. Should make it through so you guys can have all of Wednesday. I know the bad part is that means you're going to do the group work and the homework by yourself, but you guys can work together outside of class, as you know, right? You guys know that. All right. Last 2, using the range. All right. Using the range, what we do is we do one where we round everything up, and we do one where we round everything down, and we say that the answer is between the low end and the high end. Okay? So with using the range, what we do is we say, okay, 370, the low end of that's 300, the high end of that would be 400. So this is the low end, and this is the high end. And if I did 647, the low end of that would be 600, and the high end of that would be 700. So what's 300 plus 600? 900. And 400 plus 700 is 1100. And what we would say is that we would say that our range, or the range, is 900 to 1100. That is, if we were to work this problem out exactly, the answer is going to be somewhere between 900 and 1100. It sort of just gives you a low end and a high end value. Okay, a ballpark. Last one. All right, so this is estimation with multiplication division. Okay, so front end, again, means that we use the first digit. Okay, so that 386 would be the number 300. We've seen this once before, but we're going to do it here with estimation. So 300 times my 4, and what is 300 times 4? 1200. And then we're going to use the second digit as well, which would be an 8, but it really means the number 80. And 80 times 4 is 320. Now if I wanted to find this exactly, I'd do one more step because it's my last number to go with. And I can find this exactly, it wouldn't be too much trouble, right? I need to do 6 times 4. I'm just concerned with estimation. So when we do front-end estimation, we only use the first 2 digits. Okay, so if this had been a 6-digit number, we'd still only use the first 2 digits. It's a 3-digit number, we're still only using the first 2 digits. But we recognize here it would not be very difficult to find the last one and find the value exactly, right? Now I'm not quite done. What am I going to do with this 1200 and 320? We're going to add them. So this is the estimation for this 1200 and 320 is 1520. So the 1520 is the estimation over here that we're getting.
If it ever just gives you 2 on the box,
Then it wouldn't be asking you to estimate. Yeah, the directions simply wouldn't say estimate if that were the case. That's a good question. All right, the last one here is the number, or is the number about division. And it says compatible numbers. So compatible numbers is the idea of numbers that work nicely together. So what we do on this one is we take a look at the number 4132 and the number 4. And we say, okay, 4132 is not horrid. We could do the division with the number 4 here, okay. But what would it be nicer to divide it by? I mean, what would it be nicer to be divided? How could I change this number to be divided by 4 better? 4,000 would work easier, wouldn't it? It really would. I mean, I can divide 4,000 by 4 without doing any work. You can do that in my head. It's about 1,000. So 4,000 divided by 4 is exactly 1,000. But that means that this is approximately 1,000. And you probably can tell me a little bit right now, is that a high estimate or a low estimate for this particular problem? It's a little bit low. How come? Because I basically ignored 132, didn't I? I sort of just subtracted that off and said, don't worry about it. So it's a little bit of a low estimate, but it's a pretty good approximation, right? About 1,000. Any questions on that one? All right.